The broadcast is now starting. All attendees are in listen-only mode.
Hello, everybody. This is Rick Kosick with the GoldSim Technology Group, and I think we're going to go ahead and get started. Today, we're going to be talking about simulating one-dimensional advective dispersive transport. This is a pretty introductory overview of this feature in GoldSim. So for those of you who have used aquifers or pipes in GoldSim, you won't see much that's new. But for those of you who are new to the Contaminant Transport Module in particular, this will be hopefully quite helpful. So before I dive into talking about this particular feature, let's just refresh our memory of what we mean by the Contaminant Transport Module, because we're going to be talking about a feature of the GoldSim Contaminant Transport Module. So the Contaminant Transport Module is used to simulate the movement of mass through our system. And the outputs of this module are things like mass transport rates and concentrations at specified environmental locations. The module can simulate processes, not just simple mixing, but solubility constraints, advection, dispersion, diffusion, some chemistry such as sorption and solubility, and reactions such as decay and ingrowth. We're going to focus on those features that can be used to simulate one-dimensional advective dispersive transport, particularly usually in subsurface systems. So I'm going to just give a very, very quick overview of the Contaminant Transport Module for those of you who are not familiar with it. And then I'm going to discuss what are the implications of the assumption of one-dimensional transport. What does it mean if we're modeling a system in one dimension? I'll then introduce the two ways we can simulate one-dimensional transport in GoldSim, two different elements, the aquifer element and the pipe element, and we'll compare and contrast them. And then I'll close by just discussing how you can move from one-dimensional models to multi-dimensional models. So let's just do a very, very quick overview of the Contaminant Transport Module. Last month's webinar, we did a bit of a more intensive overview of the Contaminant Transport Module, and that's posted up on our website, and you can actually download that webinar if you're interested. So just as a reminder, the Contaminant Transport Module adds some additional elements to GoldSim. And these elements are going to allow us to model contaminant transport problems. There's two versions of the Contaminant Transport Module, the CT version and the RT version. And the main difference is the RT version, it includes some specialized features that you can use to simulate the transport of radionuclides. And in particular, it simulates the decay and ingrowth of radionuclides. The CT module can simulate first order decay, but it can't simulate ingrowth. So there's certain new elements that are added when you activate the Contaminant Transport Module. The ones in red are only available in the RT module. We're just going to talk about two elements that are available in both modules, the pipe pathway and the aquifer pathway today. So when we build a Contaminant Transport Module, a model in GoldSim, there's certain steps we follow. We define some species, we define some media such as air, water, sediment, rock. We then define some transport pathways through which the mass is transported. We define source terms, where does the mass start? And optionally, we can actually define some receptors who are impacted by the contaminants as they move through the system. We're going to focus on transport pathways today, in particular, two transport pathways. So when I talk about transport pathways, what do I mean? So a transport pathway represents those parts of the system where mass that we're interested in tracking is transported and or stored. So it could be a tank, let's say in a treatment facility. It could be a pond or a lake. The systems we're going to talk about today, they're going to usually be aquifers or soil columns is what we're the types of transport pathways we're interested in talking about today. When you define a pathway, you have to specify its physical properties. How long is it? How big is it? What is its geometry? And you would have to define things like what is inside the pathway. So, for example, a pathway that's representing, let's say, an aquifer would may contain water and sand. The way you need to think about transport pathways is their transfer functions. And what this means is, think of the transport pathway as a black box. Into the transport pathway, we put a signal. The y-axis here is mass rate. And we put a signal of a mass rate as a function of time into this black box, and it spits out a signal of mass rate as a function of time. And while it moves through the transport pathway, the signal, the mass, is delayed and dispersed and spread out a little bit. So that's conceptually what a transport pathway does. So GoldSim provides 5 different transport pathways. We're going to just really talk about these 2 today. These 2 are used to simulate one-dimensional advective dispersive transport. But as you'll see, we're also going to talk about cells a little bit, because cells are actually used by one of these 2 elements. And I'll explain that here in a bit. So the way we hook up a model is we build these transport pathways, and then we kind of connect them together. And the connections, which we refer to as mass flux links, describe the processes that are moving mass from one location to the other: advection, diffusion, dispersion. Okay, so that was a very, very quick overview of the contaminant transport module. As I said, if you're completely new to the contaminant transport module, I encourage you to go to last month's webinar, where I spent a little bit more time giving an overview. I spent the whole hour basically providing an overview of what the contaminant transport module is about. So now that I've given a little bit of a background of what the contaminant transport module, and before I describe these one-dimensional features, these tools we can use to model one-dimensional transport, I first want to talk about what are the implications of modeling a system in one dimension. What does it really mean when we're doing that? So if you think about a contaminant plume, a plume looks something like this. So this is looking from the top. We have some source, and as the plume moves from left to right here, the flow is from left to right, the plume, it spreads out longitudinally, right? Not all the particles move at the same speed from left to right, but it also spreads out horizontally, right? So some of the contamination is mixed in the perpendicular to the flow direction. So that's what a plume looks like. Moreover, if we were to look from the side, we also mix vertically. So we're mixing longitudinally, we're mixing horizontally, and we're mixing vertically. Now, these pictures are highly, highly schematic. No real plume in the real world looks anything like this. They don't look this smooth. If you were to, there's been experiments run where you have a well-sorted sand and you put some mass into it. It doesn't look like this at all. There's little fingers, and it's the plume itself is not smooth at all. We'll come back to talk about that later. But mathematically, when we simulate plumes, we assume that they're going to look something like this. So that's what it looks like in the real world. All right. So when we're trying to model a plume, let's say in the subsurface, in a longitudinal feature such as an aquifer, what are we really trying to do, right? Are we interested in predicting a concentration at some specific location? You may think that's the case, but in reality, that's not what we're trying to do at all. And it's for two reasons. First of all, it's not really realistic to do so, since actual plumes are extremely complex. And to say this is the concentration, you know, a kilometer from the source, you know, 20 meters deep in the aquifer, that's just not realistic for us to predict that. But more importantly, it's usually not necessary for us to predict a concentration at a specific location. And the reason is what we're often interested in when we're doing contaminant transport through a feature such as an aquifer is what we're really interested in is the mass discharge rate. How much mass is discharging into a river, into a lake, or into a well? And the concentration that we care about is not necessarily, it's often never the concentration in the aquifer itself. It's the concentration, it's the subsequent concentration downstream of that aquifer. So the aquifer has been captured by a well, and it's very, very well mixed. It's been discharged into a river and it's been well mixed. It's been discharged into a lake and the lake is well mixed. It's that downstream calculation of concentration that we're typically concerned about. When it comes to the aquifer itself, what we're really interested in trying to calculate is the mass discharge rate. How long does it take to get through the system? When does it break through? So let's now think about that. A 1D approach treats the system as a tube. That's the way you should think about it. It's as if, in fact, we could actually build a one-dimensional system. We could just put a column and pack it with sand, and then introduce the mass evenly over one side, and that's a pretty close to a one-dimensional system, right? So that's what a 1D approach treats the system as a tube. It treats the longitudinal dispersion along that tube. That's what we're modeling in a 1D system. It's ignoring the transverse and the vertical dispersion. But we can use this to do the following. If we're only dealing with longitudinal dispersion, we can model when and at what rate does the mass reach the discharge point, the well, the river, the lake. And we can see what the peak discharge rate is. And the peak discharge rate is important because that determines what the concentration is going to be in that downstream location, the lake or the pond or the stream, right? We can do that by capturing the longitudinal dispersion in a 1D system. So what this tells you is that using a one-dimensional approach is appropriate if there's a primary discharge feature for the pathway, a river, a pond, or well, into which the plume, well, not plum, into which the plume discharges, okay? So that's the key assumption of a 1D approach to simulating something like an aquifer. And in most cases, this is a pretty good assumption. These are the concentrations that you're usually interested in. A river that has a big flow, takes all the mass, mixes it up. A pond, a well in which the flow rate is very large. You're actually diluting, it's a municipal well, let's say, and you're capturing part of the plume or all of the plume, but you're also capturing other clean water and you're mixing and diluting it all together. And therefore, you know, all we really care about is when it reaches that. So that it's important you understand what the limitations of a 1D approach are. Okay, now that we've talked about that, now let's talk about the features that GoldSim uses to model systems in one dimension. Okay, there's two different elements in GoldSim that can be used to model a one-dimensional system. The first I want to talk about is an aquifer pathway. So an aquifer pathway models the one-dimensional advection dispersion, basically solves the one-dimensional advection dispersion equation. It models things like retardation. So if you've got partitioning onto a solid within the pathway, it'll capture that. It can do decay and ingrowth. It even can do things like transport on suspended particulates. We won't talk about that today, but it can model many complex processes. So what are input parameters for something like this? Well, let's just look at the dialog for an aquifer pathway. You've got to talk about what its length is, all right? How long is the pathway? A kilometer, 20 meters. You need to talk about its area. So remember, it's a tube. So this is the area of the tube. I want to come back and talk about what this really represents and how you define this area of the tube. You need to put in a dispersivity. So this is the longitudinal dispersivity. It has units of a length, it has the same units as aquifer length. It's in real world systems, there's usually macro dispersion going on, which means that the dispersivity scales with the length of the pathway. So typically you'd put in your dispersivity as some fraction of the pathway length, maybe 10% or so. We're going to revisit this number of cells here in a moment. The infill medium, is the pathway filled with some solid, a porous medium? It could be empty, in which case you're just literally modeling a pipeline. Typically you're not doing that. We're going to say, well, it's filled with some porous medium. This is important because that porous medium has properties. If you recall, for those of you who are familiar with GoldSim, you assign properties such as partition coefficients to the solids, and then this is going to be used inside the aquifer element to delay anything that sorbs onto the solid. You're basically going to retard the movement through the pathway. We need to talk about whether or not this pathway is saturated. I'll talk a little bit about this later. For the most part, you're going to deal with saturated pathways. Dealing with unsaturated pathways is possible in GoldSim, but it comes with some difficulties, which I'll mention a little bit later. And then, of course, we need to put some mass into it. The mass could be coming from another pathway, or we could just be introducing the mass directly. So let's look at a model that simulates transport through such a system. Here I have an aquifer system. It's 50 meters long, and it's got a dispersivity of 5 meters. So basically it's 10% of the length of the pathway. It's filled with sand, and I'm putting mass of 2 different species in at 1 milligram per day at the beginning of this pathway. This sand, if we go and look at the sand, you'll notice that what I've done is I've assigned a partition coefficient to one species. Species B has a partition coefficient, species A does not. So species B should be retarded as it moves through this pathway. So if we were to go and run this model and look at the results, remember we're putting in mass at a constant rate. Our results look like this, right? So essentially we're putting the mass in at 1 milligram per day. And so eventually the mass is leaving at 1 milligram per day. It's broke through. These are our 2 species. This is the unretarded species, and this is the retarded species. So it takes longer for that retarded species to get through the system because it's sorbing onto the sand. Here's an identical aquifer, but in this aquifer, instead of putting in a mass rate, I just put in a slug of mass, 1 gram of mass I put into this aquifer. If you look at those results, now you see a slug breakthrough. So this is the unretarded species, and this is the retarded species. And you can see that the retarded species is not only delayed, it's delayed, it takes longer to get through, it's also dispersed more as it moves through the system. So very, very simple model, but it shows you that we're modeling this one-dimensional system and watching mass break through the system after a certain time. The question we want to ask is, how does GoldSim actually do this? How does GoldSim actually solve this? You don't need to know this, but if you're going to use a tool, it's always a good idea to understand the basics of how we're solving the equations. And what GoldSim is doing is internally, it's actually using a series of cells, basically a series of finite volumes to model this system. And let me illustrate that. Even those of you who are used to using GoldSim may not be aware of this. So if I just walk in one time step, That's what I'm going to do right now. I'm going to start to run, but then I'm going to pause the model. I've just paused the model. You'll notice that this aquifer element now looks like a container, because it is. As soon as we started to run the model, GoldSim turned the aquifer into a container, and inside the container, in this case, are 10 mixing cells. We just created these cells on the fly. We created their volumes, how much water and how much sand was in them, and how much mass is moving between the two cells. There's even diffusion going on between these cells. If we then continue to run the model, you see that it's no longer a container. We throw those things away. So what have we actually done here? Well, what GoldSim is doing is, on the fly, it divided these into 10 cells. Why 10? Because that's what I told it to do. I said use 10 cells. All right. And I won't go into the details here, but it creates advective links between these cells automatically in such a way to properly represent longitudinal dispersion. And essentially what it's doing is we're basically creating a finite difference problem here. So this is the equation that we're solving, dCdt, for any given cell. Let's say for a cell J, dCdt is now, we're breaking it down into a finite difference approximation that's a function of the cell, the upstream cell and the downstream cell. And these are, this is the dispersivity, this is the flow velocity, this is the molecular diffusion. Delta X is this distance. We've got 10 cells. It was 50 meters long, so that defines what's the physical size of each one of these cells, and so on. And so we're just solving a one-dimensional advection dispersion equation using a finite difference approximation. That's what the aquifer pathway does. All right, the other tool that we can use to model one-dimensional transport is the pipe element. In fact, the pipe element was the original tool that GoldSim had 25 years ago. This was a tool we built originally, and then about 15 years ago, we added the aquifer element. So the pipe pathway solves the same equation. It solves a one-dimensional advection dispersion equation. It solves it in a different way. It doesn't use a finite difference approximation. It uses Laplace transforms, and you may not remember back from university, but the Laplace transforms is just a way to solve a differential equation. Kind of, you can think of it as an analytical solution to a differential equation. So it's using a different approach to solve the differential equation. You can see that the inputs are for the most part the same. You need to give it a length and an area. You need to give it a dispersivity. Is it filled with sand? Is it saturated? What's the input rate? It's got some other things that this pathway can do also. In particular, what we're going to talk about is pipe pathways can simulate the process of matrix diffusion. So matrix diffusion, if you may recall, is a process in which that occurs if you're modeling flow, let's say, through a fracture. So here I have a fracture in which water is moving through this mobile zone, and it's surrounded on each side by some rock, a rock matrix. Now, the rock matrix itself is porous. It may have a very small porosity, but it has a porosity. And so the process of matrix diffusion essentially is that as the contaminant is moving through this system right here, it actually can start to diffuse into the rocks matrix and then diffuse back out of the rock matrix. And this has been observed in experiments, and it gives a very different signal than absorption onto a porous medium gives, and you'll see that in a minute. So that's what pipe pathways can do. And because of that, they have some additional input parameters, such as the perimeter. What is the perimeter that this fracture has contact with? The perimeter would basically be this distance plus this distance plus this distance plus this distance. We also need to give it some other parameters I won't go into that define how far can we diffuse into the matrix, what is the geometry of the diffusion process. I won't get into this right now, but instead I'll just show you the results. Let's first look at the results for a pipe pathway that has no matrix diffusion, that's just basically simulating the same system we did with the aquifer pathway. Here I've done the exact same system with the pipe pathway, and if we were to look at this model, there's the pipe results, and actually here are the results of both on top of each other. So what you see is we're using two different solution techniques, but we're getting the same answer. The pipe and the aquifer can solve this system equally accurately, and we're getting basically the same answer. But now let's look at a matrix diffusion problem. And if we look at a system in which we have flow through a fracture, and we look at matrix diffusion, the type of result you get looks like this. So what I'm showing you here is a slug input into a fracture. I'm simulating a fracture in this case using a pipe element. There's two species. One of the species can diffuse into the matrix. That's the red species, and one species cannot diffuse into the matrix. And what you'll see here is that this little pattern is different than what we see with sorption. If you recall that when something is sorbed onto a porous medium, the peak literally is delayed and it's more dispersed. What we see with matrix diffusion is it doesn't necessarily delay the peak, but you get this very long tail that comes out of the system. So this is kind of the signature of matrix diffusion occurring in a system, that a species that is undergoing matrix diffusion ends to have this long tail. And the reason you can conceptually think about why we have this long tail is we're moving through this fracture perhaps quite rapidly. Some of the mass diffuses into the matrix. This clears out, the fracture kind of clears out, and then this diffuses back out of the matrix, and that gives you this kind of long tail. So matrix diffusion is a process you need to deal with perhaps when you're dealing with fractures. It comes up a lot for radioactive waste management applications. In many applications, this may not be something you need to worry about. Okay, so let's talk about these two approaches and how they're different. So pipe pathways can model matrix diffusion. That's important to understand. There's some things they can't do. They can't model a solubility constraints along the pathway. We haven't talked about solubility, but another thing that can happen theoretically is as mass is moving through your pathway, you can actually hit a solubility constraint. You say, well, how could that happen? Well, typically this could happen if you were doing a radioactive waste model. The ingrowth of some elements could actually cause them to hit a solubility limit. We can't handle that in a pipe pathway. Pipe pathways aren't also, for reasons I won't go into, they're not good at dealing with time varying flows accurately. You have to go through some extra steps to do this. In general, pipe pathways are meant for steady state flows. Aquifer pathways can't model matrix diffusion, but they can apply solubility limits, and the properties can change with time. You'll see in a minute there's still some limitations here. So as a general rule, you should use the aquifer pathway unless you need to model matrix diffusion. Use the pipe pathway if matrix diffusion is important. There is this limitation that you should keep in mind. In general, these two approaches are best suited for steady state flows. They don't need to be steady state, particularly for aquifer elements. You can still model flow rates that are changing, but they shouldn't be changing rapidly. In general, they should be changing slowly. And the reason why they can't be changing rapidly is GoldSim isn't really modeling the behavior of that flow. If you imagine that you had a phreatic aquifer where suddenly, all of a sudden, the flow rate doubled, right? Within the aquifer element, it would instantaneously say, oh, my flow rate doubled, and it would double the flow rate. In the real world, that's not how it would happen. You'd basically have a kinematic wave that moves through the phreatic surface. It would take some time to propagate that change in head, let's say at one end. And we're not modeling the flow in that kind of detail. We're just saying, oh, if the flow changes, we're going to instantaneously change it. So that's why, as a general rule, you need to be a little careful here, and flow should not change rapidly. This, by the way, also points out, and I won't go into detail here, but it points out why unsaturated flows can be tricky, right? So the example I showed was modeling a saturated system. Unsaturated flow systems are much more complicated because the flow itself is much more complicated. You essentially have along the pathway, you have the saturation changing, right? If you have a transient unsaturated flow system, it gets very complicated, and the simple approach we're using here is not capturing those flow dynamics, right? We're treating the flow in a very simple way, typically steady state or changing quite slowly. Okay, I want to come back to this this question. You recall that in both elements we had an area, right? Both elements required us to specify a flow area, all right? So how do you come up with this flow area? What does it physically represent? So a 1D pathway, as I said earlier, is a tube, right? That's what it is. It's a tube of constant area. Let's say you had a column, that we did an experiment with it. But a plume is not a tube at all. It's not a stream tube, right? In a real plume, the cross-sectional area of the plume increases as you go downstream, right? It's basically growing. Why is it growing? Because more water is getting mixed in, right? Essentially, we're mixing in water from the side here, and so the actual flow rate is bigger, and the flow area is bigger. All right, that's why the concentrations are smaller, right? As we would go downstream. So that's what's really happening in a plume. So given that, what area should we use for this flow area, right? What value should we use? Well, it turns out that the flow area is actually somewhat arbitrary. It doesn't matter. And you say, why doesn't it matter? Well, as long as the flow rate and the flow area are defined consistently, they're not going to affect the mass breakthrough, right? So you might say my area is bigger. I might say, well, I'm going to choose an area of 10 cubic meters or 10 square meters or 50 square meters. If my area is bigger, it means my flow rate has to be bigger. The flow rate that I specify has to increase. So as long as I define my flow rate through the pathway in a way that's consistent with how I've defined my area, it's not going to affect the mass breakthrough curve. So let me just show you an example that demonstrates that. So in this model, I have this aquifer element, and I've got an area of 10 square meters that we're flowing through the system. The flow rate from the aquifer element, leaving the aquifer element, is 5 cubic meters per day. So I've specified a flow rate. This is the flow rate that's leaving this guy, right? I've now created an identical element here, identical in all ways, except I've doubled the area, so it's 10 square meters, and I've doubled the flow rate, so it's 10 cubic meters per day, right? So it's got a larger area, but it's also got a larger flow rate. If I now compare the mass flux rate, the mass rate, the rate at which mass is leaving these two pathways, it's identical. Of course it has to be identical, all right? Changing the area does not change the mass rate unless, as long as we change the flow rate accordingly. So that's the take-home message on the area. The area is really somewhat arbitrary as long as you're consistent here. I will note, however, that we're also, these pathways also compute an average concentration. That's one of their outputs. This average concentration is usually not of any interest. It doesn't have a lot of meaning. What does it mean, the average concentration? It's the average concentration leaving the tube that I have defined, but I've defined my tube with an arbitrary area. Obviously, the larger the area of the tube, the smaller the concentration. And we see that here. So even though my mass rates were identical, if I look at the concentration that's exiting those two pathways, the concentration is not identical. The concentration in the pathway that had the larger A, and therefore the higher flow rate, is lower, as it has to be. And one way to think about this is, if the rate at which mass is leaving is the same, but the rate at which water is leaving is doubled, right? The concentration in the high flow has to be half the concentration in the low flow, right? But the point is, we really don't care about this, because this concentration output of a pathway is, it's not a very useful output at all. It doesn't have any meaning, because our area is quite arbitrary. It's just the average concentration leading to. One place where it would have meaning, if you truly had a tube, a cylinder, right, that you laid on its side and had water moving through, well, then it truly would represent the average concentration leaving that tube. That's not arbitrary at all. The area is physically fixed. But when we're modeling a plume, the area is not physically fixed. We're going to arbitrarily choose one. Okay, I wanted to talk about that because there's often some confusion about how the area is defined when people are using these 1D pathways. Okay, now we talked about concentrations, and the pathway, an aquifer and a pipe do produce a spatially averaged concentration exiting the pathway. As I've just noted, this concentration isn't very useful because the area is arbitrary. However, what if you did want to calculate a concentration at a specific point in space? You can do this, all right? It's of questionable value, right? And the reason it's questionable value is the reasons I stated earlier. Plumes don't look smooth, right? They're quite heterogeneous. But if we assume the plume is completely smooth, and we've got this smooth three-dimensional dispersion going on, we can actually convert a spatially averaged concentration to a concentration at a specific point in space. And GoldSim has a function to do this. There's an analytical function that's built into GoldSim. It has 11 arguments, right? Because you've got to talk about all the geometry. You'll see this in a minute. And if you take that function, it's one of the functions that's built into GoldSim, you give them those 11 arguments, you multiply it by the spatially averaged concentration, it will convert that spatially averaged concentration to a concentration at a specific observation point. So how do we go about doing that? Well, what we have to do is these are the inputs we have to give it. So we've got some pathway that we've computed an average concentration. If we really want to know the concentration at some observation point, we're going to have to tell GoldSim a lot of things. First of all, we're going to have to define the exact size of the source, because that's going to make a difference. We're going to have to tell it how thick the aquifer is. Maybe the aquifer has a top and a bottom, so things are going to reflect off the top and the bottom of the aquifer. We're going to have to tell it exactly where is the point, how far down gradient, how far over to one side, how deep, how far from the top of the system. And obviously, we're also going to have to define the horizontal dispersivity and the vertical dispersivity, because we've only given it a longitudinal dispersivity. But if we're going to try to calculate at a particular point, GoldSim's also going to need, well, what's the horizontal and vertical dispersivity for this system? So we can do this, and it's just an analytical solution. And I'll just show you an example of that. So I have this system where I've got some source of a certain size, and what I want to do is compute the concentration at a specific point. And here's the Plume function, and it's just you'll see here I've taken my concentration in my leaving the saturated zone. That's the average concentration, and then I've multiplied it by this thing called Plume, and then 11 arguments. These are the 11 arguments we just talked about here. These 11 arguments right here, and there they all are. and there's a specific point in space I'm looking to calculate the concentration. So if I go ahead and run this model, what I can do is plot those two concentrations. There's the average concentration. It's quite high. Why is it quite high? Well, I arbitrarily have a very, very small area. I just basically said it's 5 meters. It's a tube that's 5 meters by 10 meters, right? But the thing is 1,000 meters long. So this is clearly, I've constrained all this mass to a very small area. So essentially what I'm seeing here is if I constrain all the mass of the area, that's the average concentration, but that's not realistic at all. If I want to know the concentration at a specific point in space, I think this was 5 meters below the source, it's much smaller. There's the concentration at a specific point in space. So GoldSim can do this calculation, right? But I just want to alert you that this calculation assumes that the plume itself is very it looks like those pictures that I showed you earlier. It's a nice smooth plume. Real plumes don't look like that, right? So even though we're going to allow you to do this, you should question whether it makes any sense to do this. Okay, I want to close by talking about modeling multidimensional systems. So I've just talked to you about how to model a one-dimensional system. But of course, the real world is three-dimensional. So how do we model a multi-dimensional system using one-dimensional pieces? Before I talk about that, one thing we should always keep in mind when we're building a contaminant transport model is how detailed and how discretized should your contaminant transport model be? It's really easy to lose sight of this. Just because you can build a really large, highly discretized model doesn't mean you should, right? You need to start asking yourself some questions. How much uncertainty do I really have in the source? In most contaminant transport situations, your source may have orders of magnitude uncertainty. There are poor records. We don't really know what's in the ground over here. How much uncertainty do you have in the key transport properties? Things like partition coefficients and solubilities. Do you really know what these properties are? Because the pH is changing everywhere. Do we really know the pH and redox and other chemical conditions that control these key transport properties? Do you really understand the dispersive characteristics? This is what I was getting to before. Plumes are not smooth. They're extremely heterogeneous, right? So do we really understand this? Because of this, we need to keep in mind that as a general rule, our ability to predict mass transport is much poorer than our ability to predict flows. There's a lot more uncertainty in most mass transport calculations that we're going to do. And so you need to keep that in mind when you're building large models. And this is a quote. I used this in the last webinar, and I love this quote. It kind of points out a detailed model is not necessarily a good model. In fact, a highly detailed model may be a very poor model, right? So just kind of keep this in mind, that we want to make our models, build them at an appropriate level of detail. And we might be able to add a lot of detail, but if we don't have the data and if we have great uncertainty, it's inappropriate to add a lot of detail. So having said that, let's return to this question of how do we model multidimensional systems? Well, here's a simple multidimensional system, right? So I've got, let's say, a trench, and this is modeled using just a well-mixed cell. I've got some mass in here. I now have two aquifer pathways. So this aquifer pathway represents an unsaturated zone that's vertically moving downward until it reaches a saturated zone, which is represented by another aquifer pathway. So obviously this is a little toy, a trivial model, but what I've done here is now we've taken these 1D pathways, and now we're modeling a two-dimensional system, right? In fact, it's actually three-dimensional, right? We're going vertically downward here. Now we're going horizontal in this direction. So it's a simple three-dimensional system that we're creating by just coupling some one-dimensional pieces, and actually mixing cells are really zero-dimensional. A mixing cell is just a well-mixed location So by taking 0 and 1-dimensional systems, now we've got a 3-dimensional system. Here's another example of the same thing. This is the radioactive waste site where we've got some waste buried at depth. We've got some unsaturated layers that we're going to move vertically, and then we're going to move horizontally through a saturated zone. We're also going to move vertically upward to the ground surface via diffusion and some other processes. Here's a very complicated system. This is another repository system. I'll just kind of walk through some pieces of it so you get an idea of the complexity of this. So here's a repository at great depth in rock, in fractured rock. The repository consists of a drift, and then drilled into the bottom of the drift are some boreholes. Inside the boreholes are placed a waste package, and those packages are surrounded by a material like bentonite. So what has to happen here is we diffuse through the bentonite from the waste package. We then go into some fractured rock. From the fractured rock, we go into a major water conducting feature, let's say a fault. That's this. The fault then goes up to an aquifer system, which then goes into a complicated biosphere system consisting of ponds and soil and so on, right? So we've got a very multidimensional system. Here I'm just zooming in on this fractured rock immediately adjacent to the borehole. And what we're doing here is we're using pipe elements, right? In fact, we're using 12 different pipe elements with all different fracture properties to represent the variety of basically the variability of these fracture properties through this system. So the mass is moving through different fractures, each of which has different breakthrough curves and different properties that gives us kind of a summed up breakthrough curve for how long it takes the mass to move through that little fractured rock system. So very complicated system, multidimensional, but at its core built using 0 and 1-dimensional pieces. A similar approach was used at Yucca Mountain to model transport. We had vertical transport through an unsaturated zone, and then horizontal transport through a saturated zone. The vertical transport through the unsaturated zone was quite complex. It was truly a 3-dimensional grid of pipe pathways. Just because the stratigraphy was changing and even spatially, different parts of the repository had different mass source terms. And so we could still model that highly 3-dimensional system in that way. Okay, so I've gone through this fairly quickly. Hopefully it gives you an overview of these 1-dimensional systems. I want to talk a little bit about how you can learn more. So this material is discussed in much greater detail in the user manual. We have examples in our model library. If you go to our model library, there's examples of many of these. You're always welcome to send us questions. And most importantly is, you may not be aware, but a couple of years ago, we built an online course that deals with basic GoldSim. If you haven't seen it, you should. Even if you're comfortable with GoldSim, it'll take you about 4 days to go through it. It's very detailed, talks in great detail about the basic GoldSim, modeling and let's say flows. I'm in the middle of modeling building an online CT course. This is currently under construction. I hope to finish it by the end of the year. This is going to then detail how it's going to describe using the contaminant transport module in great detail. It's going to have 60 or 70 example models. It's going to cover everything you want. It's going to be much easier to learn the CT module this way than reading the user manual, which obviously is a painful way to learn the tool. So keep an eye out for this course. We will. I hope to have it up. It's a free course. I hope to have it up by the end of the year. Okay, well, thanks a lot for your attention. If anybody has any questions afterward, we have a big group now, so I won't take any questions now, but feel free to send me an email. We will post this course or this webinar to our website probably by tomorrow, along with the PowerPoint presentation and all the models I just showed you. Okay, thanks a lot, and have a nice evening or a nice day.